presentations, okay, that starting next class, okay, we will have 2 classes of which there will be project presentations. Everybody will get 4 minutes to speak about what they are doing. Now, 4 minutes is a very short period of time. How short a period of time is 4 minutes? Let's find out. Okay, I'm setting a timer here for 4 minutes to give you an example of what 4 minutes actually is. So what is the purpose of the project presentations? The purpose of the project presentations are as follows. First of all, I'd like to make sure that you have gotten started thinking about what your project is, and I think that giving a presentation is a good way to get you to start realizing that you need to have a topic, you need to know what you're doing, things like that. Second of all, I think it's a good way for you to get some experience giving a presentation. We are going to videotape the presentations. Okay, basically you'll be giving the talks here, in front here, like I'm giving it. Okay? The purpose of this is not that we're going to show the videotape on cable. Okay? Not that we're going to do anything particularly bad with the videotapes. What I would like you to do with the videotapes is to borrow it to see what you look like giving a presentation. Okay? The tricky thing is as follows. A lot of people will, when they give a presentation, end up most of you, when you give presentations, actually look pretty good. Okay, but you need to see yourself giving a presentation to be convinced of it. It'll give you some confidence. Some of you will learn that you do something very, very obvious that is wrong. Okay, that you wouldn't have realized until you've done it. Your slides may be completely incoherent, unreadable from any distance away. You may have written them in horribly fine print, or maybe your handwriting is bad. Maybe you don't speak up at all. You whisper and nobody can hear it. Okay, but when you see yourself giving a presentation like that, I claim that you can fairly quickly, in 4 minutes of watching you give a presentation, I think it is a useful thing. How many people have been videotaped giving presentations before? Okay, so a few of you. How many people have never been videotaped giving a presentation? Okay, so that is one of the reasons why I want to do this, okay, is because I think it's also good. Also, I realize you're getting to a point in the semester where you're probably getting burdened by a lot of other classes, and so you probably don't want more material that you're going to be giving exams on. So that's another strategy for having the presentations here. So that's the goal of the presentations. So how are we going to work this? Well, I am going to pass around sign-up sheets. Okay, I'm giving you out. I'm going to pass around a sign-up sheet. The first sheet is for the Tuesday slots. The second sheet is the Thursday slots. I want you to number your slots from the beginning to the end. Okay? So in other words, you can pick which day you want to do. I know everybody wants to do Thursday. I know everybody wants to go last. Okay? But I want you to go fill in the slots, and we will be having you give your talk in the order that we're given. Okay? That's the important thing as far as I'm concerned. So let me pass this thing around. Everybody has to sign up for a slot. If you're working in a group, I'll let there be 1 talk per group. Okay? If you want to do it that way. Okay? If both of you want to give a talk, that's also okay with me. Again, there won't be grades on the presentation, so don't worry about doing a bad job from the point of view of hurting your grades. But do worry about it from a point of view of, I think it's a good opportunity that's important for you. So let me start passing this around. I want you to fill in your name by a blank. Okay, and if you don't like Tuesday, the Thursday slot is on the next page. So pass that around. When this is finished going around, I want somebody to bring it to my attention so I can go and check to make sure people have signed up. Okay, the project write-ups, okay, are going to be due on May 4th, okay, which is what I said. This is after the presentation, okay? So the presentation is next week, Thursday. Then there is a last, 4 minutes. What did I have time to do in 4 minutes? Okay, not very much. Okay, but as you look here, I've basically been able to cover how many slides? Okay, approximately 1 slide. Okay, talking at a reasonable rate of speed. Okay, 1 slide can be covered in about 4 minutes. Okay, and with certain points made on it. Don't over-prepare your talks. Okay, I urge you to think about what it is that you want to say in 4 minutes. What can you say in 4 minutes? You can tell me what your problem is. Okay? Explain what your problem is, and mention what your results are. I don't believe you have time for more than that. Okay? You may not even have time to describe your results. You may be able to say, well, we're working on it. Okay? But what I just say is, realize how much time you have. Again, I'd like to give you all more than 4 minutes, but we have a class size that is, of limit, that makes it not possible. Now, the talks are going to start. Okay, question. Is that a question out at? Can I hear you? I can barely hear you. Let me just make sure that my marker is on. So hopefully, again, the voice seems to be off at Ademco. So
how are we going to do the presentation?
How are you going to do these things? Good question. What I would like to do with you guys is we'd like to do the presentations over the video thing. Okay? So the question is this thing. I want you guys to reserve a slot for the 3 of you to do it together. What is, let's take a look at this thing. When would be a good time for you guys? Thursday morning? I mean, Thursday at 2 o'clock?
But outside class time?
Okay. Why don't we discuss this right after we finish the lecture, and hopefully by then we'll be able to hear you and you'll be able to hear us.
Okay.
Okay, and we'll figure it out, but we'll do it over the TV is my vision. Okay. So what is the point here? Okay, so again, the talks, I'll want to start the talks early so we can get people going. Come the day that your talk is scheduled, come at 2 p.m. Okay? And that we're going to start the talks at 2 p.m. And the goal is to have a quick flow. People, bang, 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 and I will be setting this alarm, and the moment that that bell goes off, you go off. Okay? And the next person in line, I want to see a flow here. Okay? I want to see a flow of people. Okay? Any questions? Okay? Good. The project write-ups, just so you understand it, are again going to be due May 4th, which is the Tuesday I said it was, at 2 p.m. sharp. Okay? Again, I know that this is the end of classes. Everybody's busy. There will be no class day. Basically, we'll be picking up the exams. I'll be picking up the project reports at 2. Okay, or if I'm not here, because turns out I'll be out of town the couple of days after this. I have to give a talk I was invited to give a talk at a conference on graph theory. But so if not, there'll be someone to pick these things up, and Federal Express the project reports to me where I am. Okay, so I definitely want them at 2 so they can be picked up and mailed to me so I can get them and grade them in time to give out grades. That's an important deadline. Okay? Any questions about that? Question?
Professor, will the final exam be here?
Final exam will be here. As far as I can tell, the final exam will be here. If it is not here, there will be a sign here pointing you to where it will be. But I believe it will be here. Okay? My understanding is it will be here. Okay? The time and the date are as described in the handout book. Does anybody have, I think I may have put this on the syllabus the first day. Did anybody see if I put the syllabus? It is May 12th, sounds about right. Okay? So check it out. I believe it is May 12th. Sounds quite reasonable. Okay? Yes. I'll put it on the web page just to make sure. Okay? Yes.
I have a lecture which ends at 2:10.
What?
I have a lecture which ends at 2:10 on Tuesday.
Okay, if you can't make the 2:10, if you can't show up here physically at 2 o'clock, hopefully you're not the first one signed up for the trend. Okay, so basically come when you can and do it that way. Okay. Any questions about that? Okay. And again, it's important that you show up for the day that you're giving your talk. I won't urge you. You don't have to show up for other students on the other day. Okay, but do show up so there's a little bit of a crowd for your cronies. Okay, don't just come for your talk and bolt immediately. Hang around a little bit. Any questions? Okay. Any other questions about the presentation or anything like that? Okay. The other thing, since we've got a finite amount of, since we're not really going to have any formal class until the, until the final. What's going to be on the final? Okay. I mean, basically, the vision is going to be that we're going to have, it'll be an in-class final. There will be on the order of 6 questions on it. On the order of on the order of 6 may mean a little bit more, it may mean a little bit less. But I realize that it's going to be less than, that you only have 3 hours to do it, and that I don't want you to sort of be pressured. You probably will be pressured, but I don't want you to. And so I'm going to try to make the assignment, the problems, things that are doable, okay, in such a time. Basically, what I want you to do is, I'm going to guarantee you that there will be about 6 questions. I will tell you that there will be 1 on summations of some flavor. I will tell you there will be 1 on number theory of some flavor. I will promise you there will be 1 on generating functions of some flavor. And I promise you there will be 2 on graph theory of some flavor. Okay? So that, I think, gives you a pretty good idea about what's most important, okay, for you to study. Okay? Excuse me, what? That's only 5. So, it gives you, but 5 is a large chunk of what we're talking about. Okay? So obviously we didn't cover any asymptotics. The probability, we didn't cover too much, so I would like to, unless I come up with a really cute problem, I probably will avoid that one. Okay? So basically this gives me some flexibility to make it up, but this is basically what I think is the most important stuff that we covered. Okay? Any questions? No asymptotics. This was from a previous semester. I covered asymptotics in addition the last time I taught it. Okay? I didn't get to asymptotics this year, so no asymptotics. Okay? Any questions? Okay? So, can I move down the slide? Again, I promise you 1 problem in each of the start areas. Okay? And the ballpark is comparable to what's on the homework or the exams. Okay? That's the ballpark figure. But again, I will try to make it shorter than the take-homes. That is a definite vision. Okay? Question? On the order of 5 to 6 questions. I promised you at least 1. I promised you at least 1 for each star. There might be something else I put on there. I leave myself the option to put a little extra on there, a little different on there. But if you're telling me, no, I better spend all my time studying probability, would be a bad strategy. Okay? That's really what I'm saying. Okay? Any questions? How should you study for this? I think looking at the homeworks, looking at the exams, looking at these kind of problems, thinking about them a little bit more. Okay? Going back is probably the best general way to study for this kind of an exam. Okay? You will have access to the book. You will have access to your notes. Okay? But other than that, you're on your own.
Professor?
Any questions about the exam?
Professor?
Okay? What?
Professor?
Oh, you guys.
They're asking us to try to talk to you.
I'm afraid I can't hear you
Doesn't seem
back
like
to
he
them.
cares.
I'm sorry about this. Okay. Any other questions? And we can talk about this afterwards. Sorry about that. Any questions? Okay. What I would like to do now is talk about the last topic in graph theory that we're going to cover this semester. Okay? Which is an interesting problem on matchings. Okay? Any questions, first of all? Okay? So what is a matching in a graph? Okay, we've talked a lot about different kinds of structures in graphs. We've talked about degree sequences of graphs. We've talked about connectivity of graphs. We've talked about paths and cycles in graphs. Okay, we've talked about lots of things in graphs. A matching is a particular structure in a graph. Okay, it's like a cycle. It's a subset of edges, but it's a little bit different than it's quite a bit different than a cycle. A matching in a graph is a subset of edges with the property that no 2 edges touch the same vertex. Okay? So here we've got a cycle, a graph that is the graph in green, okay, is a simple cycle on 6 vertices. The edges in red correspond to a matching in that graph, right? These 3 edges have the property that they don't share any vertex in common, correct? So these 3 edges are a matching. What about those 3 edges, the 3 green edges? Those are also a matching, right? So if we take a look at this particular example, these three green edges form a matching because they don't have any vertex in common. These three red edges form a matching. This red edge, this red edge, and this green edge forms a matching also, right? It's a matching of two edges that don't touch each other. Okay? Here we've got another example. Okay? Okay? Here we've got an example of a wheel on 5 vertices. I claim that here's a matching of 3 edges that don't touch each other. It's 5 vertices plus a center. Okay? If you have n vertices in a graph, what's the maximum number of edges you can have in any matching in that graph? Okay, if I have n vertices in the graph, how many edges can I have in any matching on the graph? N by 2, right? Because every edge is going to touch 2 vertices, and no edge can share a vertex in common, right? So here we have a matching which has n by 2 edges in it. Here we have a matching with n by 2 edges in it. Here we have a matching with 1, 2, 3, 4, 6 vertices in it. This graph has 6 vertices. This matching has only 1 edge. Okay? Is there any larger matching in this graph? Yeah, you could get 1, 2, but that still doesn't use all the vertices, right? So theoretically, you might be able to get a matching of size 3. But is there a matching of size 3 in this graph? No, I claim not. Once you pick either one of these 2 edges, it wipes out 3 of the vertices. Okay, because somehow, if you pick this edge, that vertex can't possibly be linked to anybody in a matching because it's only connected to somebody you've already taken. So that's an argument that, in fact, this graph can only have a matching of size, well, a 2 and not 3. Okay? Any questions about what a matching is? Matchings have a lot of different applications in assignment problems. Okay? That quite often, the classic example of matching in an application is you have a set of workers who have various skills and abilities and salaries and whatnot. You have a set of jobs. Okay, so maybe we could think of it like this. Okay, we could build a graph where here we have workers. Here we have jobs. Maybe worker A can do that one and that one. Worker B is very versatile. She could do anything. Worker C, okay, is quite incompetent and can only do that one thing. Okay? Worker D, let's say, is a little bit better. Okay? The goal is, since every person can do only one job, is there a way to get all the jobs done, okay, by doing this? We'd like to assign a person to a job. Okay, is there a way such that all these jobs can simultaneously be done? Well, I think in this case the answer is yes. The one with no flexibility, we'd better take care of that person first. Maybe the person here who has 2 choices, let's say we'll, for the purposes of keeping it simple, we'll put that person there. This person there, in fact, the straightforward assignment is a matching in this graph. Okay? So the idea of whenever you want to assign something to something else, usually what you want to find is a matching. Okay? And that's why matchings are an important graph theory kind of an idea. Any questions? Okay? So for example, let's say that you are a matchmaker. Okay? You have a bunch of women. Okay? You've got to find a bunch of men. You have a bunch of men. What is a matchmaker's job? A matchmaker wants to assign each woman to one man, each man to one woman, okay? Ideally so that that couple is content, okay? So we could have an edge. The matchmaker's job, okay, is to take a look at all the men, look at all the women, talk to them, put an edge between any pair of people who might possibly be comfortable with each other. And then in order to make everybody happy, okay, or content at least, tries to find a matching, okay, such that every man and every woman are paired to exactly one person. Okay? Any questions about what a matching is? or why it's a useful kind of a concept. Okay, it's an important kind of a concept. Okay, any questions? Questions?
So now, if you have an odd number of vertices, how can we do a matching?
Okay, so what happens if we live in a world where, as some people claim, there are more single women than single men? Okay, what is the problem? Okay, you cannot obviously, if you insist that every man gets mapped to one woman, at most one woman, and vice versa. In fact, you can only have a perfect matching, okay, if you have an even number of vertices. So when we talk about matchings, there's three kinds of matchings we're going to be interested in particular. Okay? There is the idea of a maximal matching. A maximal matching is one that you can't make larger by just adding some edge to it. Okay, so if we take a look at our tree here, here we have our 5-edged tree. Here I have a maximal matching. Okay, right? There is no edge I can add to this matching. Okay, and I've got two people, one edge. A maximum matching is the largest possible matching for that graph. We showed that this was maximal, but in fact it's not maximum because there was in fact a matching of two edges that existed in that graph. We say that a matching is perfect if we have n edges in a 2n vertex graph. So in a perfect matching, like when there's perfect happiness if people match up, okay, everybody is matched up. And the only way that's possible is if you have 2n vertices, okay, and n edges in the matching. Okay? Unfortunately, perfection, as you can see, is not always possible. Okay? Any questions about that? Okay? So in a graph theory sense, we're usually interested in perfect matchings. Okay? Because they're sort of theoretically the more interesting and beautiful structure. But but algorithmically, sometimes you can't find such things, so you're looking for the largest matching you can find. Any questions? Okay? Questions?
So back to the example when you say that a perfect matching contains n edges and 2n vertex graph.
Yeah.
And
So this graph, if you had a world where, in a world where there were 5 women and 4 men, there did not exist a perfect matching. Okay? It just is not, that graph cannot possibly have a perfect matching because there's no way for every vertex to be simultaneously involved in a matching. Okay? The only way for everybody to be married up is if you have an even number. And in a world where, if you have a world where you've got men and women, and all marriages have to happen between a man and a woman, the only way you could hope for a perfect matching would be if you have the same number of men and women. If we live in a world where that's not always the case, okay, it might be possible to have a perfect matching, okay, but but not one where there's sort of this concept of 2 different groups and you have to marry from one to the other. Any questions?
so
Question.
before you added the extra woman, would that be a maximal match?
A maximal matching is one that you can look at and no one can complain to you about in an obvious way. Okay? Suppose, let's say, somebody asks you to find a matching. If you find a maximal matching, nobody can say, well, why didn't you just pick up this thing? It would have been obvious that you could pick it up without costing you anything. Okay? If I tell you, look, I'm trying to find a large matching here. If your job was to find a large matching, and you went by and said, you know something? That's the largest matching I can find. Okay? Somebody's going to look at you and say, wait a second, what do you mean? You take this one. Oh, okay. So this was not maximal. Okay? Now, what if, on the other hand, I now gave you this? Is this now the maximum matching that you can pick? And I claim the answer is no. In fact, there is still a larger one, but you have to be sneakier to find it. Does everybody see the larger matching that you could do? You could get 3. How? Well, we'll take this guy. We'll put this guy back and take which one you want, either one of these, right? Now we've got 3. This is in fact a maximum matching because there's only one unmatched vertice and there's no way you can do better than that, right? So I know darn well you can't do better than this. So that's what we mean by the difference between maximal and maximum. Okay? And if the maximum matching involves every vertex, then it's a perfect matching. Any questions? Okay, good. Now, again, matchings are an interesting thing. In fact, actually, there's a, I was recently called by a company that wanted to solve matchings for kind of an interesting reason. Okay? That just to sort of point out to you why the concept might be done. Okay? They want to manufacture very high precision parts. Okay? They make widgets out of pieces A and pieces B. Okay, I'd say maybe an A piece has a little knob here. A B piece has a little place for the knob to go. And they stick these things together and then they sell them. Okay, that's what the company does. Okay? Now, in fact, they want to manufacture these things have to fit together extremely well in their application. So what could you do? How could you do it? Originally the company said, well, the way we're going to do it is we're going to manufacture widget A's very, very precisely to high tolerance, to such a high tolerance that we know that every widget A is going to fit with every widget B, right? So they're interchangeable. That would be a good thing. But it's expensive to make things high precision. Okay? What would be another way you might do it? Well, they go to a cheaper operation that doesn't manufacture things to high precision. And they go and they buy 100 part A's. Maybe this one is big. The next one maybe they didn't manufacture it very well. The knob was smaller. Maybe they got a drunk one who did this. Then they did the same things with the part B's. They manufactured a lot of them to a lower standard of tolerance. So now its quality had clearly deteriorated. But what was the point? Their goal was to find one of these that fit with one of those. So I claim that what they really want is that it might be better if instead of manufacturing both the high tolerance, you manufacture both the somewhat lesser tolerance and then explicitly find which one of these will match with the other ones. If there's slack, the slack should go in both directions. And so ultimately what they've got at the end of this thing is, they've got a set of widget A's and a set of widget B's. They've got a graph they built. Hey, this widget A will fit with that one. This one will fit with that one and that one. This one will fit with that one and that one and that one. And then what they want to find is the largest possible matching. Okay, the largest number of pairs of useful things they can get from these crummy parts. Okay, does that make sense? Okay, so the idea of matchings come up in a lot of different applications. And algorithmically, matchings are one of the things that you can do efficiently. Most of the world for algorithms people is NP complete. You can't do anything. Okay, matchings are one of the things you can find. So you should keep your eyes out. Okay, what is there that is a matching? Okay? Any questions about that? Just as motivation. Okay? So that's why we study matchings, because there's a lot of applications and there's things you can do with them. Okay? Any questions? So, first of all, we saw that if we want to have a perfect matching, we need to have an even number of vertices. Okay? It's not true that all the graphs on an even number of vertices have perfect matchings, right? You know, let's look at an example of a graph on an even number of vertices. What's the simplest graph someone can give me on an even number of vertices that does not have a perfect matching? Does anyone? What about that? Okay. So you can have an even number of vertices and not have a perfect matching. Okay? So what's interesting, though, is that many interesting classes of graphs do have perfect matchings. Okay? So, for example, I think you should be convinced that if I give you a cycle on an even number of vertices, that has a perfect matching, right? You just take every other edge of the cycle. Okay? So all cycles have even number of perfect matchings. Has a perfect matching if it's got an even number of vertices, right? What about a complete graph? Does a complete graph on an even vertices always have a perfect matching? Well, it has to. Why? Because if it's a complete graph, one thing you could do is delete everything except the cycle, right? And now then take every other edge. So that's a proof that complete graphs all have perfect matchings if they have even number of vertices. Okay, any questions? Or the final class of graphs I'd like to show you that is interesting, that always has perfect matches, are the hypercubes. Okay? Everyone's probably heard of the term hypercube, but what is a hypercube? A hypercube is, in some sense, a cube in higher dimensions. So what does a cube in 2 dimensions look like? I claim it's a square, right? What does a cube look like in 3 dimensions? Well, it looks like a cube. Okay? What is the connection between a 2-dimensional cube and a 3-dimensional cube? Let's think about that. Okay? I claim the way you make a cube in 3 dimensions is you take 2 cubes in 2 dimensions, okay, and connect the corresponding vertices. Sorry about that. Do you agree that the way that you make a cube in 3 dimensions is to take a cube in 2 dimensions, make 2 copies of it, and connect corresponding vertices, right? This, I claim, is a cube in 1 dimension. Wouldn't you agree with that? Okay, no, not if you can't see it. That's a cube in 1 dimension. How would you make a cube in 2 dimensions? Double it and pair it up. Make a cube in 3 dimensions like that. How do you make a cube in 4 dimensions? Okay, well, you take another one of these cubes in 3 dimensions and match up the corresponding vertices, right? This one corresponds to that. 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 That is how you make a hypercube, okay, in an arbitrary number of dimensions. Okay? Any questions about what hypercubes are? Okay? How many vertices does a hypercube have in d dimensions? Let's stop and think about that. How many hypercube dimensions does a hypercube in d dimensions have? 2 to the d, right? Because it keeps doubling every number of, you double the number of vertices every dimension you go higher, right? So a hypercube has an even number of vertices, right? Does a hypercube always have a perfect matching? Let's now think about that. Okay? I claim every hypercube does have a perfect matching. Why? But we'll do it inductively. Okay? Suppose, let's say, I have a hypercube of 1 dimension. Does it have a perfect matching? Yeah. How do I make my hypercube in 2 dimensions? Well, I make 2 copies of my hypercube in 1 dimension. Okay, if I make copies of that matching, I've already matched all the vertices, right? So now I've got a perfect matching in 2 dimensions. Likewise, when I make my thing in 3 dimensions, I can take 2 of these guys. I already have the matching for the vertices with me. I claim that this construction not only gives me a hypercube, it gives me a matching on the hypercube. Okay? And so that should convince you that every hypercube, in fact, has has a perfect matching. Okay? Any questions? It's one of the reasons why hypercubes are interesting things. Okay? There are lots of interesting properties of hypercubes, which is why you've probably heard of them. Hypercubes have the property that they're Hamiltonian. Every hypercube has a Hamiltonian cycle. Okay? I mean, can anybody think of why that is? Well, this thing has a Hamiltonian cycle. If I take two things with a Hamiltonian cycle, if I put together two Hamiltonian cycles and then connect neighbors here, okay, I could build a Hamiltonian cycle by doing something like that, right? So lo and behold, it should be clear that these things are Hamiltonian. The reason why you've probably heard of them is in regards to parallel computers, okay? And the reason why people get excited about hypercubes as a graph for connecting things is that it has a lot of the good properties we want from graphs. You'd like a network to have a small diameter, a small distance from every pair of vertices, and hypercubes have that, so they could talk to each other quickly. You'd like it to be a graph have a property that the connectivity be high, so that if somebody is shooting out nodes in your hypercube, the graph is still connected, and hypercubes have high connectivity. You'd like graphs to have relatively few edges, because each edge in a network is a wire, and wires cost money. And hypercubes have relatively few edges. Okay? So these are the reasons why people build computers out of hypercubes. Okay? Is that as a graph, the graph has lots of interesting properties too. Any question about hypercube? What is the diameter of a hypercube? Okay, what is the diameter of a graph? In principle, the diameter of a graph, okay, is the is the longest distance between pairs of vertices. Okay? My claim is the following. In a d-dimensional hypercube, right, d-dimensional hypercube, the distance between any pair of vertices is less than or equal to d. Okay? So let's think what that means. How many vertices are there in a d-dimensional hypercube? 2 to the d. In fact, the number of steps it takes to get from any one vertex to any other vertex is logarithmic in the total number of vertices that you have. Okay? Can anybody see why, in fact, such a thing might be true? That a logarithmic distance is sufficient to get between any two pair of vertices? Well, let's stop and think about it. Let's just try to convince you, at least by a hand-waving thing. These two are the biggest distance is a distance of 1 here, right? Here, the biggest distance is of 2, right? 1 to get up to its corresponding point, and 1 more to get across the thing. What's the biggest distance between vertices here? 1, 2, 3. Okay? Which is namely the 2 it was before, plus 1 to get across the chasm that you built. Okay? So that, I think, is at least an arm-waving should convince you. That's probably close to a proof. Okay? That, in fact, the diameter is d. Okay? Any questions? Okay? So hypercubes are good things. You know, one should like them. One should respect them.
Professor,
yes.
Is there a relationship between isomorphic properties and matchings?
The question is, are there relationships between isomorphisms and matchings? Well, let's stop and think about it. First of all, I claim a graph could have more than one perfect matching. Do we agree that, for example, the cycle on 6 vertices has more than one perfect matching, right? I claim all perfect matchings of a graph are isomorphic. Why? Because, well, they're just sort of a set of edges that are disconnected, correct? So if I take a look at this, is that graph isomorphic to this graph? The answer is certainly yes. Okay? So in that sense, there's some kind of a connection there. But isomorphism says 2 graphs are the same. A perfect matching, if a graph has more than one perfect matching, then the matchings have to be the same. Okay? Any questions?
And how about maximal and maximum matchings?
Well, two different maximal matchings might be quite a bit different. Okay? Because again, we took a look at here. If you look back to the example that I had a couple of slides ago, which probably is now lost, you could have a maximal matching. We had to show a graph that had a maximal matching with 2 edges and also a maximal matching with 3 edges. Because the maximum matching can't be getting any larger, so that's also maximal. So there's certainly no isomorphism but necessarily between different maximal matches. Okay? Any questions? Which one? This one, about hypercubes. Any questions? Okay? So anyway, so hypercubes are interesting things. So what I want to say is I should have convinced you, I hope. First of all, that matchings are useful. There's reasons why you want to find them. Okay? The interesting thing is that there is a fairly simple way to take a look at a graph and find its a maximum matching in it. I told you that there's algorithms, efficient algorithms for finding maximum matchings. And the condition is, okay, looking for what we call an augmenting path. We say that given a graph G and a matching, a set of edges that don't share any vertices, we say that an augmenting path in that graph is a path of odd length such that the first and last vertices are not in the matching. Maybe I'll zoom this down a little bit. And the paths alternate not in the matching, in the matching, not in the matching, in the matching. Okay? Let's make that clear by an example. That may seem confusing, but it's really clear. Here I've got a matching. Correct? If you take a look at this graph, the squiggly things are in my matching. Okay? This is a maximal matching in the sense that I can't just pick any edge and add it for free, right? I'm stuck. But it is not the largest possible matching I can have in that graph. Why? Because let's take a look at this thing. I have a path that starts out on a vertex that's not in the matching, goes to a vertex that's in the matching, goes through an edge that's in the matching to another vertex that's in the matching, goes to an edge that's not in the matching, to an edge that's in the matching, not in, not in. I have a path between 2 vertices that alternates out, in, out, in, out, in, ending up, starting and ending up both on out. This is what we call an augmenting path. Okay? Can anyone see why we call this an augmenting path, or why this would be a useful thing if we want to make a matching larger? Suppose I give you a path like this. Okay? What happens if I take out of my matching the edges that were in there and add to it the edges on my path that were not in the matching? How many edges in the matching were there on this path? 3. How many edges were there that were not in the matching? Okay, well, 4. Certainly there has to be one more than the number of matching edges on the path. Why one more? Well, I start with one that's out and I end with one that's out. And in between they alternate, out, in, out, in, out, in. Okay? So what is interesting about this thing? This guy is not in the matching. This guy is not in the matching. All the other vertices are in the matching. Okay? My claim is that if I reverse the roles of it, I will have enlarged the graph, the matching, by 1 edge. Okay? And therefore, I now have a larger matching than I had before. Okay? Any questions about that? Any comments one way or another? Okay? An augmenting path is a path that if I could find such a beast, okay, an augmenting path gives me a way to make my matching larger. Okay? Any questions about that? having people see that, in fact, this is a good thing. Okay, I guess, good. Now, how do we know that we're not going to be creating any conflicts here? Okay, I think it's clear that there are more blue edges than red edges. How do we know that this reversal won't cause any trouble? Well, we know that there is no matching edge other than these that touch any of these vertices, right? Because these guys started out outside the matching. The vertices were outside the matching. All of these, so nothing was touching it from the matching. Okay? These edge vertices were all in the matching, okay, because they have edges associated with them. So there was no other matching edge. Okay, there was no other matching edge that could have touched this thing. So nobody will be unhappy if these vertices, these edges flip roles, and we get a larger matching as a result. Okay? Any questions about that?
So that graph has a larger matching than the one preceding it?
So this graph here started out with this matching here had 3 edges in it. Here, this path has 3 edges and 4 non-edges. Therefore, if I flip the role here, I now get 4 matching edges, which were exactly the 4 non-edges in my augmenting path. Okay? It's now larger. I could now go hunt for another augmenting path. But in fact, I know that I'm not going to find one because every single vertex is in the matching here. It's a perfect matching now. And so I'm done. Okay? Any question? So it should be clear. If I have a matching and somebody gives me an augmenting path, if they told me that matching was the largest possible matching, I'd say they're crazy, because of course I just showed you how to make it larger. But what's interesting is, in fact, that it's a necessary and sufficient condition. In fact, say a famous theorem in graph theory called Burgess' theorem states that, okay, a matching is as large as possible if and only if it contains no augmenting path. Okay? So that if you know how to find augmenting paths if they exist, Burgess' theorem says the right algorithm to find a maximum matching is start with any matching, hunt for an augmenting path. If you find one, do it. Hunt for another augmenting path. Keep hunting. When you can't find one, you're done. You have a largest possible matching. Okay? So how do we prove Burgess' theorem? Okay? Burgess' theorem again states that we have a largest matching, okay, that a matching is as large as possible if and only if it contains no augmenting path. Let's look at the proof of this. Let's let M prime be the largest possible matching in a graph, and N be a matching that's not as large as possible. Okay? So Burgess' theorem says, hey, M has better got to have an augmenting path, right? Because if M did not have, if M was big, M prime was bigger than M, that meant M was not the largest possible matching. Burgess' theorem says there has to be an augmenting path in this thing. Okay? Let's now prove that there has to be an augmenting path in this smaller graph. Okay? In this smaller matching. How do we do it? Let's think about the graph that is formed by what we will call the symmetric difference of the two matchings. The symmetric difference is the union of the matchings minus the intersection. That means that we're going to consider the graph formed by the edges that are in one matching but not both matchings. Right? That's what it means here. Is there going to be necessarily any edge in the symmetric difference of M and M prime? Does there have to be at least one edge in the symmetric difference? Yes. Why is that? Well, because this one's larger than that, right? So this one, if this thing has 5 edges, this thing has 4 edges, there has to be at least one edge that is in this one and not in this one, right? That is going to be in the symmetric difference. That's because it's in the union of the edges minus the intersection. Okay? So is everybody clear what we mean by symmetric difference? The edge is that's in one of them but not in both of them. Okay? Any questions? So let's now take a look at that. So here we have an example. Here we've got the original graph, okay, a graph in mind. Here is matching M prime, which I claim is the largest such beast, okay, or even, you know, it's got 4 edges in it. Here I've got M, it's only got 3 edges in it. What is the symmetric difference of these two graphs? Okay, it is going to be the edges that are in one and not in the other. So this one is in common between them, right? So it doesn't appear here. Okay, but we've got otherwise, this guy's new, this guy's new, and this guy's new, and that guy's new, and that guy's new. So this, I claim, is the symmetric difference of the two graphs. Any questions about what I mean by that? Well, let's look at that symmetric difference. Okay? If we look at the symmetric difference of two matchings, okay, what is the largest possible vertex degree we can have in this symmetric difference? Okay? What's the maximum number of edges that could possibly touch any one vertex? 2. Why 2? Well, 1 from matching M prime, 1 from matching M, right? None of these guys shared a vertex in common. None of those guys shared a vertex in common. So the maximum degree here is going to be 2. What other degrees of vertices are possible? 0 and 1, right? There's no 1/2. There's no nothing like that. Okay? So here we've got a graph that has a number of vertices. Every vertex has degree 0, 1, or 2, right? What kind of graphs can you build of the vertex degree 0 and 2? Can you build a cycle? Yeah, you can build a cycle. Can you build a path? Yeah, you can build a path. Can you build anything else? No, now you've got something that's of degree 3, right? So my claim is, if I take a look at what this graph is going to be, it could be made up of paths and cycles. Okay? It can't be made up of anything else. Does everybody agree with that? Okay? Because we know the degrees can't be too big. Further, is everybody with me so far? That I think is clear. Further, I claim that every path on that graph has to alternate between edges from one matching and the other matching. Right? Does everybody agree that you can't have 2 green edges in a row? Why not? Why can't you have 2 edges from the same matching next to each other on a path? Well, then it wouldn't have been a matching. So what does that mean about our cycle here? Suppose I've got a cycle. Okay? Could I have an odd number of edges on a cycle in that graph? Okay? Because if I did, what would happen? It was red. What color did this have to be? Blue, red, blue, trouble. It can't be either red or blue. Okay? So I claim that we have the following property. We have in this graph here, everything has to be either an even length cycle or a path alternating red, blue, red, green, red, green. Okay? Agreed? Well, let's think about it. If we have a cycle, okay, of even length, how many edges does it have? More red edges or green edges in it? No, it has to have an equal number from both matchings. We agreed that M prime was going to be bigger than M, right? It wasn't, this was a smaller matching. So where did the extra edge go? It couldn't have gone into a cycle, so it had to have gone into a path. And so therefore there has to be some path that has more red edges in it than green edges in it. Right? If I tell you you've got a graph that only consists of isolated paths, okay, you might have a graph that went red, green, but that would then again mean that we had the same number of edges of each type. In fact, there has to be somewhere one more of these edges than one of those edges. Therefore, there has to be some path that has more reds than blues, even though they're alternating red and blue. And this, my friend, is an augmenting path. Okay? So therefore, there has to be an augmenting path to boost the matching higher. Okay? That's the interesting thing about Burgess' theorem. Okay? We just proved that there has to be an augmenting path in any graph, okay, for any matching that isn't optimal. Any questions about that? That's a cute proof, so you should look at that and like that proof. Okay? I encourage you to understand that proof. Okay? Any questions about it, one way or another? Okay? So matching now, I have basically shown you an algorithm that enables you to find matchings. Okay? And I've shown you that they're a useful thing. So I think we now know a lot about matchings that are interesting. Now, most often in matchings, the most important special case of matchings that you see all the time is bipartite matching, where the graph has the vertices can be two-colored. That's what we talked about bipartite graphs last time. Two-coloring meant that the vertices were partitioned into two classes such that there was no edge between vertices in the same class. Right? So if that was true, then, and again, this happens a lot when, let's say, you want to match, again, men to women, tasks to equipment, people to jobs. Okay? Bipartite graphs come up in lots and lots of different applications. Okay? So in fact, most of the time when you want to find matchings, okay, you would, it reduces to being you do it in a bipartite graph. Bipartite graphs are special types of graphs. Burgess' theorem, we didn't talk about bipartite graphs at all. So in fact, for any graph, okay, Burgess' theorem holds. So in fact, you now know how to find a bipartite matching with what I showed you how to do before. Okay? And in fact, you can actually find bipartite graphs, matchings of bipartite graphs easier than general graphs. But that's maybe not so important now. Okay? But the idea of bipartite matching is very important. Okay? Any questions? Let me show you an interesting sort of theorem in graph theory related to bipartite matching. That's actually kind of a useful and interesting kind of thing. Suppose, let's say, I have a bipartite graph defined on boys and girls, okay? And I would like to make it be the case that every boy gets married to some girl that they know, okay? We agree that you can't have that in an ideal world, you have a perfect matching in a bipartite graph. You have an equal number of boys and girls, right? Then it's possible to have a perfect matching. Okay? If we live in a world where maybe there's more girls than boys, okay, some girls are stuck, okay? But on the other hand, the best one can hope for, okay, is a matching where the smaller color class, every one of them is married off, right? This is as perfect a matching as you can hope for. A bipartite graph where the vertices are imbalanced, right? And in an ideal world, it's not imbalanced in everybody. We have a perfect match. The most perfect we can get is indeed a perfect matching. Suppose we want to now know a condition to guarantee that a bipartite graph has a perfect matching. Okay? Some bipartite graphs have perfect matchings, some don't. Okay? What could we do to guarantee it? What can we say about a graph such that we could guarantee that it has a perfect matching? Okay? And there's a famous theorem in graph theory called Hall's marriage theorem, which says that a perfect matching, or what we'll call a perfect matching, in the case of them being equal numbers of men and women, it would be a perfect matching. And if not, it's as perfect as possible. We say that there is such a matching will exist if and only if every subset of boys knows at least that many girls between them. Okay? Let's think about it. Suppose, let's say, we had a matching like this, where we want to be able to marry all the boys off to all the girls, such that every boy gets married to one girl, and every boy gets married to a girl that they know. Obviously, you could randomly say, well, the A's get married, the B's get married, but Chris doesn't know Chris. Okay, so that wouldn't work. Okay. Does this graph here have a perfect matching? Okay, I claim the answer is no. How can I convince you very clearly that there is no such perfect matching? Well, let's take a look at Bill, Chris, and Dave. These three people know between them exactly 2 women, right? How are we going to marry all 3 of these people off to two women, such that every woman, both of those women, only marries one guy? Okay, it clearly cannot happen. Okay? So my claim is that, okay, if there's going to be a perfect matching, it better be the case that if you have any subset of K boys, and you take a look at all the girls that they know between them, they had better, okay, know at least K girls among themselves, right? If not, you're stuck. Then there is no possibility for a matching to occur. Okay? Does everybody agree that this subset condition is clearly necessary for there to be a perfect matching? Okay? Any questions about it? Okay? In fact, I claim that this condition is sufficient. Okay? Hall's theorem, which actually I don't think I'm actually going to, we're running a little bit late. I don't think I'm going to actually prove Hall's theorem. Okay? But Hall's theorem says that this condition, that a certain number of boys have to, that a perfect matching will exist if every subset of boys knows at least that many girls between them. Okay? It should be clear that that's necessary. It's not clear, so clear that that's sufficient, but there's a proof in the notes if you're interested. Okay? Any questions about that? Can anybody think of an application for why one might want Hall's theorem? What might make Hall's theorem a useful thing? Okay, it's cute to talk about. It's always fun to talk about marriage and things. Okay? But why might, can anyone see an application potentially of Hall's theorem? Okay? What might be why might Hall's theorem be a useful thing? Okay? Does this give us an algorithm to test whether or not a graph has a perfect matching? Okay? Does this condition give us a fast way to tell if a graph has a perfect matching? Okay? What would we have to do to use Hall's theorem? Okay? We could take every single subset of boys, count how many girls they know between them, and see if that number is bigger than that. Right? If I have n vertices here, let's say I have B boys and G girls, how many subsets are there here of boys to test? 2 to the B. So in order 2 to the B times G, each time I'll have to look at all this, maybe all the girls. Anyway, in order 2 to the B time, I could test whether Hall's condition is true. Does that sound good? Doesn't sound good to me. Okay? So algorithmically, Hall's theorem does not seem to help you in any way. Right? The other theorem, the idea that you're looking for augmenting paths, that will give you a good way to find matchings. So, on the face of it, Hall's theorem doesn't seem very useful, at least not for algorithms. But one reason why it might be useful, at least one reason why I once found it useful in an application, is as follows. Suppose, let's say that we want to, I have a bunch of items. Let's say that we consider the parts situation. Okay? Suppose, let's say that I have here, remember we were back to the situation with that company that we were talking about, where we want to pair off parts. Suppose I have, let's say, 50 different part A's. Okay? And I want to now come along, I come up with new part B's. Okay? I come up with a part B. And I test it. Can you possibly fit against that? Can you possibly fit against that? No. Can you possibly fit against that? Can you possibly fit against that? Okay? I now know that that part B is, I now know what the possible connections are. I could now bring out another part B. Test what it's adjacent to. Okay? Bring out another part B. Okay? And let's say maybe this one's going to be connected to that, and that, and that. Maybe I'll have another part B. And this one maybe is going to be connected to that, and that, and that. Does this graph necessarily have a perfect matching? Well, it does have a perfect matching. But how do I know when I can stop? I want a condition under which I can stop adding new parts. That's easier to test than actually finding the matching. My claim is the following. If I have here, let's call this thing n part A's. If every vertex here has degree greater than or equal to n, if every one of these n things, or these 50 things, knows at least 50 other parts, okay? What do I now know? If I take any subset of vertices, there's going to be at most, something less than 50 vertices in this part, right? If each one of these guys knows at least 50 guys between them, then in fact I know that every possible subset of these guys is going to know, okay, at least that many of these guys. Okay? And so that is a sufficient condition for there to exist some kind of a matching. Okay? That's really why I might be able to use it. It's something that will gives me a way to quickly guarantee that a particular graph has a matching. Then I can later go about and find it. Okay? Any questions? It's a different kind of condition. It's a condition on classes of graphs. Do these graphs have perfect matchings? And sometimes you can prove that a class of interesting graphs has such things. Okay? Any questions about that? Any questions about matchings in graphs in particular? Okay? Any questions about these? Okay. the last thing I'd like to talk about, okay, is a problem related to matching that I claim is the most important algorithm problem any of you will ever solve. Okay? Okay? And it is the problem of finding the largest one of a set of numbers. Okay? So if I take a look at these numbers, 15, 96, 35, 42, 7, 13, and 84, which is the largest one of them? 96. Okay? That doesn't seem like such a hard problem. In fact, this is a terribly hard problem to find the largest one of a set of numbers. If I give you numbers one by one and make you decide which is the largest number without going on. Okay? So suppose I do the following. I give you the number 75. I'm telling you that I'm going to show you 5 numbers. Is 75 the largest number I'm going to show you? You can either take it now or lose it forever. Okay? Is it the largest number that I'm going to show you? Who here says yes? Who here says no? Okay? Well, let's say no. Is 14 the largest number you're going to see? Well, no. 33, no. 88, is 88 the largest I'm going to see? Okay. Who says yes? Who says no? Yes? Well, you lose, okay? In fact, 92 was the largest one you've ever seen. Okay? So the problem is, actually, given a set of numbers that you're going to be seeing, you know you're going to see n of them over your lifetime. They're coming to you into some arbitrary order. How do you find the largest number in that set? Okay? This, I claim, is the most important algorithm problem you will ever solve. Why is that? Okay? Because it relates to a problem of matching. Okay? How do you find the optimal spouse? Okay? What is the situation that we would like to discuss here? Okay? In general, okay, the way that you find a spouse, at least the way that I did, okay, was that you meet somebody, you evaluate them for a while, and then you have to make a decision. Is this the person I marry? Okay? Or do I tell the person, no, you're not the one I'm going to marry? Okay? Ideally, what I could say is, I might want to marry you, but wait here while I look at some other people. Okay? Does not work. Okay? At least I never found that worked. Okay? So the question I have for you now is a strategy question. Okay? Over the course of a dating lifetime, okay, you will date n people. Okay? You can just figure out that basically by how many times, how fast you date people, how fast you evaluate them, which is a personal thing, and how long you would possibly hope to go dating. Okay? If you can date 5 people a year, and you want to date for at most 20 years, then n is 100. Okay? So the question now goes, how, without peeking ahead and without being able to go back, do I determine what's the largest one that I can do? Okay? This, I claim, is exactly the problem that we have. Again, matching Hall's marriage theorem is one way. This is a slightly different situation, because here you're not explicitly in conflict with other people. What is the strategy that you should use to find the optimal spouse? Okay, can anybody give me an idea for what a reasonable strategy might be? Okay. Anybody have any proposals? Okay, for how you might go about looking to maximize your chances of getting the best one? Okay. Okay, what would be a reasonable strategy to try to do? Okay. Well, my claim would be that the basic optimal strategy, okay, is going to be something like this. Okay? I will sample some fraction of people, okay, date them and reject them to get some kind of an idea as to what the pool is like. Okay? Suppose, let's say I have n people that I could date, and I use the high school sweetheart strategy, where I marry the first one I see. What's the probability that that be that I end up with the best one of the n? Okay? 1 over n. What if I use the reluctant bachelor strategy, where I put this off as long as possible? What's the likelihood I end up with the best one? 1 out of n. Okay? What if, on the other hand, I use the date the first, okay, n over 2, and reject them all, okay? And now pick the first person that's better than the best person I have ever seen, okay? What is the likelihood here that I end up with the best person overall? Okay? Can somebody give me a scenario under which I do end up with the best person overall if I reject the first n over 2 people and then go on to pick the first person better than anyone I got? Under what condition will I? Can someone give me a situation under which I get the best one? When the n plus 2 by 1 is the best, that's certainly true. Okay? But how often will that happen? 1 out of n times, so that's not a good enough reason to believe it's going to work out well for me. Under what condition will I win here? I will win if the second best person, okay, is in the first half of the pool, and the first best person is in the second half of the pool. Right? Does everybody agree with that? Because once I've seen the second best person, I'm not going to stop for anybody here until I see number 1. Right? So what's the probability of this situation happening? Well, there's a 1/2 chance number 2 is in the first half, right? And a 1/2 chance that number 1 is in the second half. Okay? So I claim that with a probability of at least 1/4, okay, using this strategy, I end up with the best. Okay? And in fact, it's a little bit higher than that. There's other situations where I might win. Like, for example, suppose that the best person in this first half was number 3, and number 1 occurs better before number 2 here. Right? That way I'd also win. Okay? So in fact, I claim that a sampling and then pick better than the best is the optimum strategy to maximize my chances of getting the best. Okay? And I don't want to go through the analysis. Okay? But in fact, actually, you can prove that the optimum strategy is not when you reject a half of them, but when you reject approximately 1/8 of them, where E was 2.718. Okay? 1 over E was about 38% or something like that. So the right strategy, if you want to think of it that way, okay, is to reject the first one, to date and reject the first 1/8 of your life, and then pick the best that you can after that. Okay? Any questions about that? Okay? I won't say I'll leave it for you as a homework. Okay? But it's something to think about. Okay, what's the probability, though, on this strategy that you never marry anybody? That's sort of the catch here, if you want to think about it this way. What's the probability that you never marry anybody if we wait for the 1/8 of the life and then take the first person better than anybody we've seen so far? Well, 1 over E, if the top person happened to be in the first 1 over E slot, then you spend your whole life looking for someone better, and you ain't going to find anyone better. Okay? So there is actually a risk with this strategy. Okay? If you insist on getting number 1, there's a good chance that you go home, okay, alone. Okay? So anyway, any questions about this? Again, this is a strategy I used, and I got married about 1.5 years ago, and it works. Okay? Any questions? Okay. So first of all, what's the status of the sign-up sheet? Who has the sign-up sheets? Okay, who here has not signed up for a presentation on the sign-up sheet? Go back to the sign-up sheet, sign up for a presentation slot. Okay, see you guys next week. You got 4 minutes. I'll see you guys next week for your presentation. Thanks a lot. Okay.
Professor?
Can you guys hear me now? Or?
We can hear you. Can you hear us? Hear
Problem is I can't hear you.
Can you hear us?
Let's think about this thing. Tell you what.
Email?
Yeah. Okay, tell you what. Why don't we say this? You give me a call in my office at, give me a call at 4 p.m. Okay, I will be there. Okay, one of you all to get in the room.
They can hear you.
Right, I definitely can't hear that.
But they can hear you.
Okay, good. Thanks a lot. Great.
Hey,
These guys are good. Okay, let's talk.
I'm not sure. Who is it? Who is this guy? I don't have this name. Yeah.
Okay. Let me okay, let me see what I can do with that. I don't know what that means, but I'll keep that in mind.
This one.